Okay, my talk is a little bit of change in pace from solid-state physics and production of diodes and frequency doubling and so on. My name is Daniel Murnick, and I'm a physicist with a particular interest in production of ultraviolet light and producing ultraviolet light efficiently and effectively. And I want to talk a little bit about getting broad spectral coverage and comparing the different lamps that are available and that people might want to work with. You said it works. It doesn't.
Right.
Oh, there we go. Okay, so the UVC, or the germicidal band, is a very tiny fraction of the total electromagnetic spectrum. You're basically considering the range from about 200 to 280 nanometers. We've seen many talks today, and there's a lot in the literature about germicidal effectiveness. And the effectiveness is not uniform across the band, with large variations depending on the microbe that's being irradiated. There's a significant literature on germicidal action curves, as they're called, but the experiments are hard to do, and there's not complete literature. More recently, in the last 20 years, particularly in groups at the University of Colorado and the University of Alberta, there has been more data produced. And I point out on this slide a very useful data summary of germicidal action curves for a variety of pathogens that has been updated by James Bolton and collaborators every few years. This is a typical germicidal action curve using a normalization that I believe was first introduced by Professor Bolton, which normalizes to the deactivation at a certain wavelength. And not surprisingly, the wavelength chosen is 254 nanometers. So the number 1 on the y-axis is the 100% efficiency for mercury. And as we change wavelengths, as you go greater than 1, that wavelength is more effective. As you go below 1, that is less effective than mercury. And for this particular subtilis spore, as you can see, as you go below 240 nanometers, the effectiveness gets much higher than it is for mercury. The dashed curve is the absorption curve, the absorption spectrum for DNA. So clearly, at shorter wavelengths, you're doing more than having the light absorbed by DNA, and we've had discussions of that. It's primarily due to protein disruption, which disrupts the species. And here are some more data for, this is for the adenovirus and MS2. And in particular, on the left-hand side for the adenovirus, as you go to very short wavelengths, the effectiveness goes up by factors of 5 to 10. You really can't go below 200 nanometers, even though we've seen data this morning at 185 nanometers, because below 200 nanometers, light is heavily absorbed by air and water, so it won't reach what you're after. And in addition, there usually aren't good transmissive glasses for the very short wavelength. Above 240 nanometers, as this slide shows, there's not too much variation because mainly the effectiveness comes from the DNA absorption. So for wavelengths between 240 and 300, for a variety of species that are in this curve, which is from Beck and all, you can see that there's not much change, but at the shorter wavelength, there is a big change. So given these curves, and you're looking at different pathogens, viruses, bacteria, spores, and so on, what wavelength for a given application would one want to use? Clearly, it depends on your application. 254 nanometers, I call the gold standard, so narrow light from mercury vapor. And it's proven effective for most microbes in air, on surfaces, and in water. The range from about 200 or 210 to 240 is the shorter wavelength range, which has a shorter range in matter, and it's very effective for viruses, better than mercury, a little less effective for bacteria. But the shorter range in matter is a plus and a minus. It's positive because it's less damaging to the skin and eye, but it's negative because it can't get through much stuff, including water. The range from 260 to 300, where most of UV LEDs have been, is similar to 254, but as you get to the longer wavelength, you're lower on the DNA absorption curve, so you need more power to get the same killing. The other possibility, which I'll talk about, is a broad spectrum lamp from 220 to 280, which may be best for most applications, especially when you don't know what the next pandemic will be and what wavelength would be most effective. And if you have a broad spectrum lamp, there also is, in some cases where it's been studied, but might be for others, synergy. Because polychromatic light sources can attack both the DNA and the proteins. I have a quote from a paper from Beck emphasizing how polychromatic sources may be the most effective. So what I've done is define a figure of merit for a given spectral output relative to 254 nanometers. And the figure of merit is simply an integral of the activation curve for what you're after times the intensity distribution as a function of wavelength. Realize that the total power you need to eliminate or bring down 1 log, 2 logs, whatever your needs are, depends on the total fluence, which is the power times time. So if you have a low power source, it takes longer to eliminate what you want. Now I'll compare the lamps. Low pressure mercury lamp radiates at 254. By definition, by my definition, the figure of merit for mercury is 1 for all pathogens, because that's our standard that we're measuring against. We know the good point about mercury, it's a very efficient lamp. Efficiency is 20 to 30%, but it has a lot of negative problems. Mercury is toxic. The lamp is very temperature sensitive, and for that reason it has a long warm-up time, and it's not amenable to rapid electronic control. And it also is limited in the power density in the lamp due to what atomic physicists called radiation trapping. The 254 nanometer light can be absorbed by the mercury, so it limits how much radiation you can have in a given volume. Dielectric barrier chromium chloride lamp radiates at 222. Typical efficiency is low. It's only 1%, could be a little higher, could be lower. It does make use of a somewhat toxic gas, halogen. Chlorine is in it. Figure of merit for 222 is greater than 1 for most pathogens. That's good because it means you need less time or less energy to eliminate what you're after. But be careful, the short range, especially with aerosols, limits it reaching its target. So as we saw in some of the talks today, the curves that you get in the laboratory with a plate and a beam for what I call a figure of merit, the improvement on mercury, in real world situations, it's sometimes not quite as good. UVC LEDs are long wavelength, though we've heard research in the last hour on pushing to shorter wavelengths, and that's good, but they're already at low efficiency, and theoretically the efficiency goes down as you go to shorter wavelengths. They're very good for small applications, and wound healing and so on. And I have spectra that are published for commercially available LEDs, and I'm going to compare, as an example, 265, which is a commercially available LED. Figure of merit is about 1 at 267 nanometers. That's larger than, well, it's about the same as mercury. But as you go to longer wavelengths, the figure of merit goes down, which means you need more intensity. Now, the broad spectrum lamp, which was invented at Rutgers University in my laboratory, is based on phosphors with a highly efficient 172 nanometer vacuum ultraviolet source. It has two broad peaks. Its major peak is at about 225, 227 nanometers, and it has a secondary peak at about 262 nanometers. By the definition of figure of merit, it's the order of one or a little bit greater for all pathogens because it's covering so much of the wavelength scale. And for those who are concerned about above 240, where there's a big change in the absorption curve of matter, about half the power of this lamp is in the range below 240 nanometers. These curves just show relative spectral outputs. The figure of merit is taking the action spectra and multiplying it by the normalized intensity curve. So each one of the red curve is the intensity is normalized to 1, so 1 watt or half a watt, but you have to have the same power per lamp. And you notice mercury, 100% to 254. The krypton chloride is about 20% of its light is exactly 222. The LEDs are broader, so no wavelength has more than 8% of its lamp. And the large spectrum lamp, it's 1 to 2% per unit wavelength over about 100 nanometer range. And I show the blue curve is a typical action curve. But I show on the left a special curve for the adenovirus where it's the right-hand scale and it goes up to 5 or 10. Now, for a given application, it's more than the wavelength that's one is interested in. It's the efficiency, the geometry, can it be electronically controlled? Everyone's interested in the costs, the operating costs, the capital cost, and the environment it's going to be used on, and its effect on the environment. That's one of the problems with mercury. So are you using air, water, surfaces, what temperature range? Will there be human exposure? Is it recyclable? I could spend a lot of time comparing all of these lamps, but it depends on your application. What I did do was produce a comparison table, which is crude, giving what's good and not so good about mercury lamps, krypton chloride, LEDs. The bottom three columns are my figure of merit, and you can see they're all near 1. By definition, mercury is 1. Krypton chloride is 2 to 10 for MS2 and the adenovirus. However, for some species, like the cryptosporidium, it goes less than 1. You're much better off with the longer wavelengths. The LEDs are typically around 1, and the spectrum lamp is 1 to somewhat greater than 1 for most species. It's slightly less than 1 for the cryptosporidium as well. Toxic materials, the spectrum lamp is fully non-toxic and fully recyclable lamp, so it has no negative environmental effects. All of the lamps except mercury can be controlled electronically. Typically they can be dimmed, turned off and on very rapidly. I'm told my time is ending. The cost is very important. That's the last comment the column mentioned. The mercury lamps are low cost. They've been around for 100 years. They're manufactured in bulk all over the world. The krypton chloride lamp, a relatively high cost per watt. I mean, you want to compare cost per watt, not cost per lamp. The UVC LEDs are very high and coming down. They still will be very high per watt. And at this point, the spectrum lamp is moderate cost. So I hope there's questions. That's